So I'm going to tell you about a few scientific adventures we had in the framework of the MIST collaboration, of which Edith is the PI, and thanks to her, we are all here. So Edith has the idea, when looking at these type of images, as Pierre Lesaffre showed us already, that these small bioluminescent plankton, which light up in very strong shear, are the witness of the very strong dissipation structures that you see in the turbulence on this beach. And so she coined the name coherent structures of intense dissipation extrema, seasides. So I'm going to tell you about seasides in MHD simulation. And what you see here is just a projection of the dissipation in an MHD simulation over what we hope is the plane of the sky. So this is the outline of the talk. I'm going to give a short introduction on intermittency. Then I'm going to tell you about the seasides in MHD simulations, and then a few other fun stuff that are rather new for me now. So first, a disclaimer. The galaxy is a complex subject, and I'm going to skip self-gravity, skip cosmic rays, skip dust issues, and heating and cooling will not be treated either, because I'm going to show you only isothermal simulation, which means you have very strong heating and cooling, in fact. Okay? So, how to characterize turbulence? You look at this image, and your brain already processes a lot of things. Even though I didn't put any caption, you know this is a puff of smoke. You even know that it's probably going this direction because it's getting more diffuse. And this is an image of a passive scalar projected on the plane of the sky. And so this is good news for us astronomers, because there is a lot of information on this image which we should be able to retrieve to get at what this turbulence is, okay? What the fluid motions is. Turbulence, in fact, I don't even know what this is. It's very vague as a word, okay? So here is a collection of all we know about, almost, I'm exaggerating, but all we know about the statistical properties of 3D incompressible homogeneous turbulence. So it started with Kolmogorov, who inferred the power spectrum. Then Kolmogorov himself realized this is not enough. We need to go to a more, the power law is not enough, and the dissipation is very intermittent. It happens in very localized places, and he coined another, a new model, Kolmogorov 62, which amounts to giving the probability of these increments for the velocity. Increments are simply taking the difference of a field at, in between 2 points which are separated by a given distance, okay? And finally, the Hofart-Karman-Monin equation, which is an analytical expression, the only mathematical analytical expression that we have on turbulence, almost, and which relates the third order structure function, so the average of these increments to a certain power, to the average amount of dissipation in your box. So this is what you see when you look at the statistics of these increments over various scales. You see that there is, so these are the, first, these are the PDFs of the increments, and they are all divided by their variance, okay? So that means we have filtered out this power law dependence. We are only looking at the next order. That's what intermittency is, in a way, okay? And that's only one way to see it. You have also the intermittency exponents and the multifractal stuff that I'm not going to talk about. It's asymmetric. This is linked to the fact that this average of the third order of the third power of these increments is non-zero, okay? So it's very subtle. For MHD, 3D MHD turbulence now, we already don't have the slope of the spectrum, okay? We have these two models, and if you want to have a fair discussion, but a long one, on which one you should choose, you should read that reference by Alex. The intermittency scaling has been derived for these two choices. First by Politano and Pouquet and Grauer for the Hiroshnikov-Reichnan case, and for the Kolmogorov case, it's Paul Diref in 2002, but the arguments of these two papers are fairly similar. It's just the slope that enters the equations, which is different. So here we are for the introduction. Now the seasides. So I've been running a set of simulation, of MHD simulations with Doomsdays, which is Ramses for the dummies, a very simplified version of Ramses without AMR. Salut, Warman. And when you integrate, so first I devised very subtle ways to measure what is the actual dissipation of the scheme at a given point in the box. This is the dissipation rate, which I can now measure locally. And then I integrated it over the box to see what would be if we had a tracer which would react immediately to like the plankton of Edith, which would react immediately to the heating. This is what we would see, okay? By integrating it over the plane of the sky. Now, we can look at some, we don't have this tracer. We have the radial velocity sometimes, which we can measure if you have a spectrum of some molecules. We have the total integrated column density. We have sometimes the Q and the U-Stokes parameters of the polarized light emission. And these are plane of the sky integrated things that I try to build proxies of on my simulations. I looked at the increments of these things, the small scale increments to be more precise. And if I do contours of the small scale increment, you can see that they delineate the position of the seasides on my simulation. So that might be a way to localize observationally these seasides. The next thing I did was to try to play the game that people did in numerical 3D experiments and in actual experiments for incompressible simulations, and look at the statistics, the PDFs of these increments for now the whole range of scales. And what you can see if you now plot the structure functions, which I now defined for the projection of these things. So basically what you do is you take the average of the absolute value of the increments to a certain power at a given separation length, okay, which we call the lag. If you look at for various powers, the evolution of the structural function versus the lag, you feel that there is some kind of a power law in a very narrow range, which is maybe the inertial range of my box. But it turns out that in '96, Benzi discovered the practical, practical thing that almost everybody since uses, even though nobody knows where it comes from. If we scale, instead of the lag, we use the third order structure functions, which is supposed to be linear, but for that incompressible homogeneous turbulence, then it straightens these power laws and it extends it to the dissipative range. Lags, small lags are this way, dissipative range and large scale range. And this holds as well here.
What is the meaning of that inequality, that kind of suffix on the structure function?
That's just the lags are in fact not, the lags could be vectors. I could decide to take the difference in between 2 points which are separated like this over my whole image. What I do is I average all the increments for a corona. Isotropy, exactly. It's very common to do that. So this is really surprising. This is a result which holds for hydrodynamics. I have now projected things which are not the velocity, and I don't even have a very good reason to say that this should be linear in air. Nevertheless, this seems to be to hold. So there is some kind of extended self-similarity in the projected things of my in my boxes. So I use this to plot an intermittency exponent. So now what you see is just the exponents of these, the slopes of these things for with respect to the order. And this is what intermittency models will predict typically. And I compare it to several models, two of which are the ones for MHD. They are here and here. So this one seemed to work better. And these are observations by Edith and Pierre Lesaffre on the Polaris and Taurus cloud. So, okay, they match, but it turns out, as you will see later, that increment statistics are not that good probes of the textures, okay? But, okay, maybe this is interesting still. Now, let's look, we have the full box. So let's look at these seasides in more detail. What my PhD student Thibaut Richard at the time did is to devise a way to first isolate these structures and then look in every point of the box. We have a way to decide in which direction is the gradient of the state variables the strongest. And along that direction, we scan, exactly like one of the satellites of Olga or Julia, okay? We are on this satellite and we cross we will cross the point where on that line the dissipation is strongest. And we can decide whether these things are Parker sheets, slow shocks, fast shocks, rotational discontinuities. This is isothermal MHD, so we don't have much choice for these things. And then we can look at the statistics of these seasides. And what we observe is that when we vary the Prandtl number, the statistics don't change. They change much more when we vary the initial conditions. This is one turnover after the initial conditions, I should say, where the statistics have more or less stabilized. Okay? I forgot to mention that these simulations are decaying simulations. I don't have any forcing. Okay? I start with some configuration, I let it go.
The ABC flow is three-dimensional, right?
Yeah.
But the Ozak tank is two-dimensional.
Yes, but okay. And you put an Orszag tank initial conditions in the three directions, and that's the way I start my flow. Orszag tank like, yeah. This is the this is just it was a way to devise a large-scale initial conditions, which would give some non-trivial behavior. Okay, and the two things differ by their magnetic helicities and cross helicities. They were not chosen by at random. So this is a very strong result, I think, because the fact that it doesn't change with Prandtl number, to me, means that these initial conditions, they set where these seasides will be, their positions, and the Prandtl number just changes the width of these things in magnetic and velocity things. So in a way, you can build the same turbulence, if you will, by having the proper macroscopic structure functions with the proper velocity for the shocks, proper current sheet orientation and stuff. And then you can paint on it the microphysics of each of these seasides. And so that's why in the next section, I'm going to talk about an attempt with Jean-Baptiste Durive to predict the positions of these seasides. And so now I'm going to look at the equations without dissipation. So this is Burger's equation without dissipation here in 1D. And Jean-Baptiste noticed that if you Taylor expand this at 0 and you use the Cauchy formula to obtain to express the nth derivatives of this that you will get, then you can obtain a closed form at any time. The solution of this equation can be written like this. This is very powerful. Now you have a direct formula for an arbitrary initial condition at a given t, which will give you the solution. Okay, so we think this is new, but if you know about this, please tell us, because we have dug the literature, but maybe not enough. Why isn't this? This is Benjamin. Benjamin's mouse is hiding my eye. It turns out that this formulae, we noticed that they can be generalized for 2D and 3D. And for hydrodynamics, at infinite Mach number. So I'm going to show you an example in the next slide for 2D HD at Mach infinite. But our agenda was actually to look at approximations of this Taylor expansion to find good approximations. In this case, we found exact solutions. This was a very good surprise. But we are going to use this to find good ways of approximating the Taylor series. And Jean-Baptiste and I are now skimming the mathematical literature on this series, which you find in quantum mechanics and cosmology. It's a lot of work has been done on this, and so we think that we can find powerful approximations. So now you see on the left 2D infinite Mach number at HD that I coded with a good enough scheme with the Lax-Friedrich-Riemann solver. So this is hydro. I need to compute every step to get to that to the solution I want to find. And on the right is just the equivalent formula, the analytical formula, which will give you the solution at arbitrary time. Okay, now there is a small drawback. There is an integral contour in there, and this is a double integral, so it's not that easy.
We don't know what the colors are.
This is the log of the density.
But the white and the yellow are very different?
Yes, there is a glitch here, because technically the density is infinite here in the analytical formula, but we can actually recover. We know exactly how much mass is in between. In fact, there are two shocks in here, face to face. Okay, but
you are producing a singularity, of course.
Exactly. Yeah, and so this is not okay. So the last part of the talk is about synthetic turbulence. Imagine we could build a random field which bears all these statistical properties I told you about, okay? But at a much lower cost than having to run the same simulation, okay? So this attempt should at least help understand better if we fail or achieve what exactly characterizes what we call turbulence, okay? So previous attempts were fractionated Gaussian fields or fractionated Brownian motions, as they are called sometimes. They are just Gaussian fields with a given power law. And you know that these are very bad. They don't look like turbulence at all, okay? These were started with Manuel Brot at that time. And then there are two classes of models. One, some models focus on the deformation of the field, like Chevillard in 2006 for HD, and an extension of that model that we did with Jean-Baptiste more recently. And models which focus on the advection of the field, like Rosales and Menvaux for HD. You just start the field and you advect the velocity with, you start from a Gaussian field and you advect the velocity with itself for some time. And this gives you a good approximation, apparently. And Subedi et al. Generalized this to MHD. And then Lübke et al., I should say, combine a bit of the two because they do the same as these guys, or slightly better way of advecting the two Alsacer variables. But they start from an already non-Gaussian field, which is a key to achieving. And these guys are the first ones who managed to get coherent structures in their simulations. So now, this is just to advertise the Jean-Baptiste, the big cross C thing that we did. Now I'm going to show you the latest results we have for the a generalized framework for any, almost any, but not any, I shouldn't have said that, partial differential system of equation. Here exemplified for 2D incompressible hydro. So if you start with this field for the vorticity, incompressible hydro is determined by the map of vorticity. So we start with the Gaussian field for the initial conditions, and we run 300 standard steps of a simulation to do the reference. And this is just a teaser. This is what we get with only 4 steps of our method. Okay, and this is right now about 17 times faster, but we haven't optimized this. It could be much faster. So I'm already out of time? Okay. So maybe I will skip this. This is the generic form of the equations, but it incorporates many different kind of systems up to self-gravitating ones. But we start to validate it on 2D hydro. And the principle is that when you filter this system of equations, you get a system which depends on the velocities filtered above that scale. So if you start to with an approximation for the evolution at the larger scale, then you will have the scale above your heads, and you are in good order to proceed with the next thing. And the idea is that you have only one step to run for every logarithmic scale. Whereas in a classical simulation, what you do is n step of all scales, in fact. Okay? So the cost is reduced by n over log n. And this is, for instance, the Musca 3D would scale almost like the full hydro 2D. Okay? And so you gain a lot of power. I shouldn't have said that because Patrick will say that I'm now destroying the environment. So these are the classical statistics, and you can see this is the initial conditions in green. The condition you achieve after one turnover for the actual simulation. I ran 30 of them for 30 different realization of the initial conditions, and I averaged these things to compare them. You see the power spectrum is very well reproduced, so Musca is in red. This is only one step of Musca for one turnover. Energy transfer functions and entropy transfer functions, which depend on this slight asymmetry of the PDFs I showed you at the beginning, so which are very sensitive to these things. They are fairly correct, except for the increments, which you can get better if you do 4 steps instead of 1. This is the map, and that's why I said these increments are not that good to constrain the structures, the actual structures. Okay, I'm done, and I'm gonna flash my take-home messages. Thank you.
Questions? Yes.
Thanks, Pierre. This is super cool. I'm wondering what you do with, let's call it, caustics crossings and things like this, right? You must have crossings of lines of information transport where your thing breaks down. So you cannot go beyond it. I guess this is why you have stopped your movie at this point. How do you go beyond?
Very good question. In fact, the idea is that indeed, if you integrate too long, you have shell crossings, and you can't do that. So the idea is to integrate only for one shell crossing time, or an approximation of that time. If you are at a given you want a field at this time, okay, but you have what controls the velocity and the deformation from the upper scales at that time, then you have a good idea of how trajectories will either escape from each other or cross each other, like some kind of a Lyapunov exponent of these fields. Okay, so you know that if you change these initial conditions here by some small amount and you integrate from here, it doesn't matter really. Okay, you will. If your Lyapunov exponent is that long, then you can only choose at random the initial conditions here. You don't need to choose them that far, okay? Because basically here they will be random again.
But sorry if I ask again.
Yeah.
I mean, these caustics will become everywhere and space filling, right? I mean, this is the reason why almost no one uses adaptive mesh refinement for turbulence, because eventually there is the overhead of the AMR is not justifying the still need for small time steps. So I'm wondering how you deal with this, unless you smooth the small scales to prevent it in some way, no?
The small scales don't intervene because I'm filtering them at a given point, okay? So I'm retaining only the large scale part at a given scale, and that one has a smooth kind of Lyapunov exponent. And I don't need to select initial conditions at random at this scale for longer than this characteristic evolution time scale. So a key point in that model is to choose what is the correct evolution time scale that I pick up, even at a given position, not only at a given scale.
And then the small scales fill up again. Smart.
Yeah, okay. But it turns out that you can do only one step for a given scale.
I'm sorry, we have to move on because there is a public session at 6. Is there another question? Yeah.
You've set up a kind of for your synthetic fields, you've set up a kind of sort of Turing test for them, where you try to determine whether or not you can tell the difference between them and your real hydro simulations.
For human being.
Well, exactly. I mean,
that would be cool. I haven't, but that's a cool idea.
Oh, but I mean, it's, in a sense, you've done that because you're creating more and more things to try and distinguish them, and it's harder and harder to distinguish at each level. Do you think there's ever a situation where it passes the Turing test at all levels, but is still cheaper to run than a hydro simulation? Does this make sense?
You mean?
Where it agrees with every possible test you can throw at it, it looks exactly like Turbulence, run with a real simulation, but is somehow still cheaper than a real simulation.
It's already the case. That's one.
Exactly.
Yeah. Okay. I've also looked at WST coefficients, which are very strong characteristics of textures.
Mm-hmm.
Maybe you can show them, and they fulfill that test. How does this work? I will show you later.
Okay. All right.
Okay, but
Yeah,
I've looked at at much more stringent statistical characteristics than these ones,
Okay.
and they are good as long as I do these 4 steps. That's why I'm looking at this one.
So cheap simulation will mean more simulations if I follow.
Yes.
That's so cool. Let's thank Pierre again and.